like the official start time, but it's awesome to have you here. You've been going through the Grokking deep learning book too, right? You're having some lunch, so you won't be talking. Yeah. Okay. Well, then I guess I can't ask you too many questions. Maybe once really quickly before you go back. How far are you in? What chapter are you on? You're doing the MNIST dataset. Okay, so you're at the end of chapter 5. So I have, man, it's been an up and down week with that. So we left off last time. Oh, you're on chapter 7. Okay, so you're a little bit farther than me. I sort of paused on the MNIST dataset, feeling like, okay, I can. I'm just going to work on this until I get it training and like working properly. And last stream, we ended up setting up the training and then setting up the testing to see like, oh, how accurate is it? And it was never updating. Like we thought maybe the weights weren't updating. No, we got the weights updating, and still the prediction was the same. I read the entire thing in Python, and I got the same result. It was sort of never updating. I played around. I found that if I put the testing for all the data set inside of each loop through, each time it tested one data point, then the test changed, but it was just sort of random, staying around like maybe 20% at the most, and then going back down to like 8% or 3% sometimes. And so finally, I gave up and decided to move on and read chapter 6. And at the beginning of that is what we're going to do today, which is the streetlight problem. And then a little bit into it, it had the revelation saying, "Oh, by the way, your the neural networks that we've been showing you how to make, they won't work, or at least they're broken in a fundamental way that won't allow them to train and then test properly." So basically, what we have is a neural network that is, as far as I can tell, is trained for exactly what we put into it. Meaning that if I hand it any unknown data, it's going to be an incredibly low chance that it's going to guess correctly. The book sort of talks about it being random, but I think it's more of just the correlation isn't really there. It has to be the exact same input for it to guess the correct output. And then the end of chapter 6, which I haven't finished yet, but I'm getting close to that, talks about how to fix this and how to make a neural network that actually will do what we want to do. And that is basically having two neural networks, having the input of one neural network go into the output. No, the input goes into one neural network. The output of that neural network goes as the input to the next neural network. And the output of that neural network is the actual prediction that we're having. And I guess we could have like multiple layers of those for more complex data sets. But apparently that is the solution. And there's some things that we need to do to make that work. So we'll see how far we get today. We'll probably catch up to where I am because I haven't like done very much reading because I spent far too much time just tweaking the broken neural network that never was going to work, because that's kind of what I thought was going to happen. So let's start a new file here. So you close, you open, you. All right, what do we have here? So we have all of our basic stuff here. I'm going to just start chapter 6 because there's a lot of stuff in there now. And I think our functions, we can leave those out in this top directory, and we can use them for the most part. I did find a NPM module that is close to NumPy for Python. So it's mainly made for working with numbers and matrices. So I might sometime switch over to that. What book is this? Let me show you. Camera big. Oh, right when I was refocusing. The book is this. It is Grokking Deep Learning. And I've had a very interesting relationship with it. I don't know if Katali has the same sort of feelings with it. It's been up and down. Like, oh man, this is really cool. It was like, why are you doing this book? So it is very interesting. So I'm going to go back until the beginning of this chapter, and we're going to do the streetlight problem. All right, so here's touch streetlight.js. All right, so here's the idea. Const inputs. I guess I'll just put streetlight configurations. So each configuration is going to be, oh, camera's still big. You're right. Thank you for that. I'm not used to the entire like switching scenes, so I don't even have like shortcuts up, which I probably should do if I wanted to do that more often. All right. Thank you, Phil. Also, good morning. All right, so here's the streetlight configurations. 1, 0, 1. And what the idea of this is that imagine that we're on some kind of alien world, and we walk up to a cross street, and there's this light, but instead of like red, green, and orange like we're used to, it's flashing just random, like seemingly randomly, but then people definitely know how to walk. And so these are the configurations that we notice in like a, I don't know, hour-long time as we stand there. 0, 0, 1, and then all ones. It's not too many of these, so we're almost done. And finally, 1, 0, 1. And as we notice that on, let's see, const streetlight results, a streetlight walked. Maybe did walk. And so they people walked, and it's interesting. They have this be a matrix too, but a matrix of only a single output. So they walked on did not walk, did walk, did not walk, did walk, did walk, did not walk. So as a human, we're very good at creating a correlation between the did walk array here or the matrix here, and the streetlight configurations matrix. We can probably figure out what the answer is, but of course that's not what we care about. We care about, can we write an algorithm that it will tell us what the configuration is? So we can just go ahead and create our basic algorithm here. Let's begin our import. Let's see, import. I guess it's not import. We're not using TypeScript or oh, what's the other one? Webpack. So it is const require. There we go. Okay, so I guess the first thing they have us do, like we need to have, like, we have our weights, we have our inputs, we have the correct outputs, we need the weights. And this, because this is a 3 inputs coming to a single output, we need 3 inputs then to match these 3. So 1 input for you, 1 input for you, and 1 input for you. But we don't need like another weight for each of these. So this is really just going to be, they actually have a numbers set here. I'm thinking we could probably just do like math.random. Just set these up randomly. They give us weights in a book, but I'm thinking that, like, in a normal data set, we wouldn't know what these should be. So we're just going to set them randomly. And we then also need an alpha, our limiter. So we can start with 0.1 and see if that makes us like blow up over, and we need to go down or up. All right, so we have that. So now we want to probably set, if we want to like work on just the first one to make sure we get this correct, we'll just say our current input is streetlight configurations of 0. Current output, current expected output is equal to did walk of 0. And then we're going to loop through this and do our normal thing. So we could do a for loop. That count equals 0. Count is less than 20. Count equals count plus 1. So first up, we need to get the prediction. So const prediction is just a single one. We don't have a neural network. I guess, like, do we put a neural network in the? I think we put a neural network function in the deep learning functions, but that was for a multi-in, multi-out. This is a multi-in, single out. So what I'm going to do is we take all of these and we're going to dot them with all the weights, and that will give us our prediction. So we need a dot. No. Dot. Also, I don't know why that was auto finishing like that for me. That's interesting. All right, so we have dot. Is it now like actually going to try to autocomplete for me in that way? Oh, it's because oh, that's silly. I included a P5.js snippet, and that is very I don't even have P5 installed here right now. All right, let's do this again. Don't do that. All right, so dot, our vector 1. Well, so our vector 1 is going to be our current input. And our vector 2 is going to be our current weights. And so that will give us our prediction. Once we have our prediction, we need to get the error. So a const error equals, I think we have calculate error, but it's not going to work exactly the way we want it to. And I think my work actually just sent me a quick email. Hold on, I need to check that really quickly. All right, they're waiting for someone else to reply. Perfect, then I will continue on. We had a critical fun thing yesterday, so there's a little bit of fallout this morning from that. Let's see, const error is going to be our prediction. So this is going to be math.pow. It's going to be our prediction minus the expected output. So that would be the current expected output. Current expected output is an array. So I need to just grab the first item from that. And of course, bring this to the power of 2. So that will set our error. And we have our delta, which is simply the prediction minus current expected output of 0. Okay, so then we want to get our weighted delta. That's taking our delta and multiplying it by the inputs. Because it's we need it to match the weights. So I think this is, and delta is a single number now. We need to have this be I think a scalar vector. Is that how? Oh yeah, because they're using NumPy in their examples, it sort of gets a little bit interesting. But yeah, so we have a scalar here and delta, but we have a vector in weights. So we need to multiply delta. So do we have scalar vector multiply? We do. So this is going to be scalar vector multiply. Our scalar is the delta, and our vector is the inputs. It's actually not input, it is current input. So that gives us the weighted delta. And that's going to be a vector. We now need to limit that. Limited weighted delta. We do that by multiplying this vector by the scalar alpha. So it's going to be another scalar vector multiply alpha and the weighted delta. So this gives us a vector here and a vector here. So now we're just going to say weights equals, and we're going to do a vector subtract. Vector subtract, we're going to take the weights in the first position and the limited weighted delta in a second. And that should update the weights, and it should just continue going through here. I should now be able to console.log prediction current expected output all right, so let's give this a shot. Let's see if we can get it to run. Put you over here, you over here. Node. Oh, I'm not in the right directory. Assignment. Oh, constant. Yep, you need to be a let now. Okay, so our prediction we see is 1.039, and then it's going down towards 0, and it's not going to reach it. So if I go even further to like 40, it shouldn't pass it. We're just keep on coming closer and closer and closer to our prediction. So the idea here is that we'd be able to put a configuration of a streetlight in, and then say, okay, here's the weights that we've previously trained you on. Tell me, what am I allowed to walk or not? And if it's closer to 0, closer to 1, we're allowed to walk. If it's closer to 0, we're not allowed to walk. Of course, we just trained only on one data set. So then the book then talks about how to learn the entire data set. And that's what we were attempting to do last time, which is we're going to go over this 40 times in here. But inside each iteration over and over again, we're going to do another loop, except we're going to grab one streetlight at a time, train on that once, like one pass, update the weights, go through the entire thing. That will be our inner loop. And then we hit this outer loop, and so we repeat that cycle 40 times. Hopefully, we'll get an error that a very low error. So we need to track the total errors. Okay, so we have total errors here, and essentially I want to for each through the streetlight configuration. So this is now going to be our current inputs, but we also need the index. We need this index so we can get our current expected output. So in a way, we don't need this line anymore. That's going to go away. Our current expected output is now going to come into here, and it's going to be our did walk of index. And in a way, I could probably just make this a little bit easier, and it's index of 0. I'll just leave it what we had originally. It works. All right, so we have our current expected output now, and we can kind of do all of this stuff inside of here. So we have current expected output, we have our current inputs. I'll just be consistent with what we had before. We get our prediction by dotting the current input and the weight, so this is no different than before. We get our error, which is exactly the same as before. We get our delta, our weighted delta, our limited weighted delta. We update our weights. Before we're not going to console log here. Instead, we're going to total errors equals total errors plus our error. So that's going to allow us to track to see how close we're getting overall. So theoretically, and I think, does it even... I mean, it has us logging this out. It also has a, okay. Interesting. So the book, to sort of show this off, has console log in here, where we're saying prediction, and this is our prediction. And we also have console.log, just to sort of help with this. They don't actually have us putting our expected output here. So expected output, current expected output. And then at the bottom here, so after each loop, or I guess this is yeah, this is going to be inside of this loop, outside of this loop. So that's right here. We're going to have another console.log, total errors. So theoretically, we should now be learning the entire data set. And we can see the total errors going down, which is good, which means that it's like, it's learning this properly. And so when our expected output is 1, our prediction is close to 1. When our expected output is 0, our prediction is close to 0. So, I mean, that's a good sign. It seems to be learning this. And so that's when the book threw that bomb saying, yeah, there's no correlation. If we attempted to have testing data, this wouldn't work. And we would get, we would not get as high of a rate as possible. And they said it's called overfitting, which is our network just trained for this data set and is now like that's all it can do. So now we're getting to the point where I've caught up. I haven't done this next exercise in Python yet. So this is going to be interesting. Katali, you're back. Welcome back. Also, I just remembered I didn't have this set up, so I'm going to add it. How's it going? Well, I got the streetlight problem, the basics of the streetlight problem, but now we want to start actually making it learn by adding in that second, the second neural network. So if I could, this is where like my understanding, hopefully me explaining it will help me understand more. And if I'm wrong, please let me know. Because I want to learn. I want to learn and improve this. So we have this as a single do this with NumPy, but like switch over to Python and do it in NumPy. I'll need to transpose matrices and some weird stuff. Well, it doesn't, like, I think at the chapter 6 stuff, I don't need to do that craziness, right? At least I don't think I need to. Let me, look at the final example of code in the chapter. Oh, just one, put it all together. So this is going to be so much fun to watch me read this, I bet. Import NumPy, set a random seed, set the riilu and riilu to deriv, like create those functions. Set up the inputs, set up the outputs. There's that dot capital T, which I'm not sure what that is. Set the alpha and the hidden size, which I'm not also, like, that's the outputs of the first network, I think. Set both weights for the first network and the second network. Loop through 60 times. All right. Actually, you know what? Instead of, maybe Katali, you're right. Let's because this is probably boring for us to look at. Let's try this. I'm going to touch streetlight. That is transpose the matrix. Okay. I haven't read that part, so I'm wondering if it tells me what that is. Streetlight.py. So let's just do this in Python here. Not dot. It doesn't explain it. Great. That's also not what I wanted. Thank you. There we go. You searched it online? Yeah. What is transpose? Transpose matrix. The transpose of a matrix is a new matrix whose rows are the columns of the original. This makes the columns of the new matrix the rows of the original. So we have 5, 4, 3, 5. Oh, it's a rotate. So it rotates like that. I don't know if that reversed in the camera, but it takes it like that and rotates over. So this is still 0, 0, but this becomes 0, 1, or I guess like 1. Yeah, 0, 1. No, 1, 0 if I'm going down like this. I guess oh man. It's the second array, so 1, 0. And this is 2, 0. Okay. That might actually be interesting to write. So I would have to write those functions if I want to do this in JavaScript, which I kind of do in the end want to do this in JavaScript. So let's look at this. This is one of the disappointing parts of the book, that it doesn't really tell us that it's doing that. It just says, just do this, and it works. All right, so if I also don't know what the random seed is doing for us, which makes me a little bit sad. And the book uses the shortcuts of NumPy to sum vectors and matrices. Yeah. which is also a little bit, you don't mind that? It's not as bad because the first part of the book doesn't do that. So we learned what it's supposed to be doing first, and then it switched to the shortcuts, which is okay, except I'm trying to do these in JavaScript, so I don't get those. But okay, I'm not that itself is not the sort of more negative thing. It's the introduction of the transpose without mentioning that that's what's happening at all. It only makes sure you get the same numbers. I guess like if I don't have that at all. Oh, because right. If we create a random weights, that's why. Viable clan member, hello, good morning. All right, so let's come back to this. We're gonna update this, and we're going to. Well, okay. I'm sort of going back and forth. We're going to do this in NumPy just as they have this, and then we're going to translate it over to JavaScript. So import NumPy. I don't like to rename NumPy because it's short enough name. I like to sort of see what I'm doing with it. I was going to say it looks like machine learning, then I saw the title. Yeah, this is I'm learning deep learning. So I'm still very, very, very basic with it, but I'm taking you all on the journey with me. So they have the random seed. I don't really feel like doing that. I'm okay with it taking more or less steps than it did for them. So they're creating this function, riilu, which they explain as you take in a number x, and what's interesting to me is this is like return x is greater than 0 times x. That is very interesting. I want to play with that. So like 3 is greater than 0 is true. But if I take that and multiply it by like 2, you get 2. If I multiply it by -1, I get -1. The function sets all negative numbers to 0. False times a number is 0, but could open, let me try this. False times -5 is 0. Why did this return -1 and this otherwise? All I can say is that this is basically just plain tricks. Returns 0 in the case if x is less than 0. When I write it, I'm not going to write it like that because all numbers are true and 0 is false. Yeah, still, yeah. Also, is it greater than? It is greater than. Okay, so it's all negative numbers to 0. Oh, that's a graph of the riilu function. Okay. I guess we could take a look at that. Let me go grab it. It's from O'Reilly. So this is the graph of the riilu function. So starting with 1 is obviously like 1, 2, 3, 4. So it's going up like that. everything below that, so like -1 and down below, is just 0. It just gets reset to 0. And I guess it's easier to see it. You can also implement with max, 0, and x. I mean, another way to implement it in JavaScript is used a... I always forget the name of the inline if statement. Oh, I forget. Ternary, yes. Ternary, thank you. I can implement it with a ternary operator as well. That would be pretty easy and a lot easier to see what's going on. So I might do that. Okay, so we have that. We have our alpha, which we're setting to... That's the other thing that I'm confused a little bit about. He spent a lot of time, like the book talks about how alphas are generally just set to a factor of like 10, like 10, 1, 0.1, 0.01, 0.001, and so on. And then you can tweak it from there, but it never really goes into like why you should tweak it. And so he throws out a .2 here, for example, and I don't know why there's a .2. This is the limiter. I mean, I can set it to .2, but I wonder if .1 would work just as well and maybe not as fast. And then we have our hidden size, which he's setting to 4. It's because the way that the gradient operator works. Well, it's because we're multiplying it against the delta to scale the delta. If alpha is very small, it'll take an eternity to converge. Well, yeah, so I get that. I guess you just tweak up. Like if we start with 0.1, it's like, oh, we're good. Let's like go to 1, and then that's too much. Then we're like, oh, let's just count up by 0.1 each time. Have you played with the TensorFlow playground? No, I haven't used TensorFlow yet. Or at least not really. So I'm going through this first to learn the machine learning or the deep learning algorithms natively, and then I'm going to switch to TensorFlow as I will understand what's actually happening, and we'll be able to debug things when I do things wrong. So that's my plan. We need machine learning to get the alpha value. That's an interesting one too. All right, so then we have our street lights. So I'll put these in here too. So street lights. Right, we're doing this with a numpy.array. And I think there's only 4 in this one. Okay, so that gives us our 4 size matrix. I'm not gonna be able to look at that YouTube video right now, but maybe, I don't know. All right, let's continue on. Walk first. Okay, so then the end result. And that's very interesting. So we're transposing the truth. So walked. Oh, I deleted too much. I did it way too much. There you go. Did walk verse stop. All right, so this is going to be another numpy array. Interesting. They have us do this. Written out, it's an array of a single array of the outputs. 1, 1, 0, 0. And then they have us transpose it. So that is a little bit, that's fascinating. I want to print did walk verse stop. Okay, so this prints out exactly what we put in here. If I put the dash T on, it then transposes like that. It just puts each one into its own array there. When I'm looking at the, let's see. Wait, does it even finish this? It doesn't even finish this code. That's fun. I wonder if it does it with this second array here, so that way you can just grab it. You loop through. I mean, it doesn't really make sense. Let's just try one. In a final example, it only uses one array. And then if I do that, well, here's the thing. Transposing a single array doesn't do anything at all because, well, it's just a single array. It needs to be a matrix in order to transpose it. So that might be one of the reasons why they did that. Still an interesting choice. Moving, just tried with two arrays, it broke. Ah. Yeah, that's another thing I've noticed in this book. There's some parts of it where the code is wrong, has bugs in it. The input really upsets me. What I mean by input is the author constantly uses input equals and then will like something, and input is an actual command in Python, so that's will cause bugs. So then we set the first set of weights, which I'm not a huge fan of their naming convention here. So they use weights. I guess I'm following along with what they have. So we'll rename it in JavaScript. 0, 1. All right, so what's happening here? We're doing 2 times numpy dot random, and then interesting, a second parentheses in here. I'm not sure that works. 3. And then we're going to use the hidden size. And after this, -1. So I need to print this out. Hacker, good morning. Input is only command in Python 3. If the tutorial is in Python 2, the input command would be... Oh, is that true? Oh, I did not know that. I haven't used Python in a long time. So I just looking at Python 3, I'm like, well, of course that makes sense. Okay. That's why he uses it. Oh, he's sending a tuple in. That's what's happening. Okay. So let's print out these weights. So this gives us a full matrix now. And of course, these are all random numbers. Now, I can tell you sort of like what's happening here. The 2 times is a very interesting way of like repeating things. So if I were, let's come back into Python 3. If I were to say like array of 3 times 2, then I get this array times this. So if we look at this, 2 times, what is it doing twice? It's the overwriting of numpy. Oh, interesting. Let's see if I don't include 2 times. I mean, it's hard to tell because they're all random. Many times, and they're all negative. They're all negative because I'm subtracting 1 from each one. It's doing a scalar vector multiply. Okay, so this is multiple steps all happening together at once. Thanks. This is many steps happening at the same time here. Well, maybe not that many. We're creating this vector, which has down 3, that's this right here, and has our hidden size, which is 4 across. So if I change this to like 5, then we're gonna get 5 across and 3 down still. So that's what's happening there. The -1 is doing a matrix scalar subtraction. So it's taking whatever is in each of these and subtracting by 1. And I think the 2 times is happening first. So basically, this happens first, create the matrix. Take the matrix, multiply it by this. Then take that result and subtract it by 1. And it gives the weights that look the way that the author wants them to look. And it looks like it's between -1 and 1. That's all we're getting at. So we can write a comment in here. Create a matrix, and that's going to be, in this case, 3 height, hidden size, width, with each value between -1, and 1. So that's what's going on there. And then we want to do the same exact thing. 1 and 2. And this is going to be literally the same size except, no, it's not going to be the same size. Okay, I'm wrong about that. We're going to start the same. So numpy.random. We're going to pass it in the tuple, but in this case, the down size is going to be our hidden size. And the across is just going to be 1. So if now we print out weights 1, 2, we now see that it's 1 across and 4 down. All right. So then we have our layer 0. So this is I don't think I need to comment this one because I can use this comment to sort of figure out what this is doing. Then we have layer 0. So and we're going to get the streetlights of 0. So get the first set of streetlights. So that is this right here. Then we have layer 1. We're going to do a riilu, numpy ... layer 0 and weights 0, 1, and then layer 2 layer 1 and the weights 1, 2. Not the best naming convention here. The layers don't really make that much sense. I guess they're just trying to show in a graphic that's on the page what's really happening. But let's see if we can like figure out what's going on. So here's our input. This is simply the inputs that are going to be going into the neural network. So it's 0, 1, 1, 0, 1. Then a few things happen here. We're going to dot layer 0. So that would be 1, 0, 1 with this first set of weights. But what's interesting is that the weights is the entire matrix. Did I miss something here? For some reason, I didn't think that you can dot a matrix with a, can you dot a matrix and a vector? Well, we could try it. So even though this is happening here, I want to try print. There are 2 matrices. Well, streetlights of 0 is not a matrix. It's just this array here. So layer 1 is an array, isn't it? and weight 0, 1 is a full matrix. So I don't know if I have that wrong or if I wrote it down wrong. It's not transposed. Let's try this. Numpy dot we're just going to have streetlights of 0 and weights of 0 and 1. Interesting. Okay. So the result here is a flat array with 4 long, which kind of makes sense. That's the hidden layer. But so it's taking these 3 with all of the, oh, it's doing something to these first. And then that result is going out there. So you can dot a vector and a matrix. Oh, you know what's happening? I think it's going down this way. So it's dotting down, but it's doing something to this first. I wonder if it's averaging it. If it's averaging these. I bet we can. Let's try this. Numpy.dot. If I set you to be like 1, 2, and 3, and you to be, let's start with the basics. So like 4, 5, and 6. We know u should be 4 plus 10 plus 18. That should be 32. 32, okay. Now, if I ask it to dot like one more here, what will happen? Right, okay, so it needs to be the same length. That's kind of what how I know that dot works. But if I take a matrix here, and I have 1, 2, and 3, 4, 5, and 6. Let's just do 2 of these. We should get 2 outputs. So an array 2 long. Three long, value shapes. 3 and 2, 3 not aligned. All right, so it needs to be the down on the matrix needs to be the same as the width in here. So it needs to be 3 in this case. So 7, 8, 9. And it gives us this 30, 36, 42. So let's see if we can figure out this math here. Is it dotting these 3 together? These 2 together? No, because this would be a much smaller number than 30. So it's doing something to the matrix first. It's dotting the vector in each row in a matrix. Oh, so it's this. So that's what's happening. Okay. 1 times 1 is 1, 4, 9. So 1, 4, that's 5, plus 9 is 14. I'm just doing the ones right now. So I guess then plus, because we have to get to 30. Just search for it. Matrices do matrix multiplication. For n-dimensional matrices, it is a sum product over the last axis of A and the second last axis of B. Wait. So it has to create a new vector and then sum that. Is it summing down here? So this would be 1, 5, 12. So create a single vector of, the output is how wide these are. But the sum has to be this wide. All right, you got a link for me. Let's take a look at this. All right. Note that the dot product is 1 times 11, so down like this, plus 2 times 13, this one. So that, then the third one, if there is a third one. Okay, that's interesting. Wait, come back. So it has 2 here, but I have 3, so it has to be 3 long. So it's u times u plus, so that's going to be 1 times 1 plus 2 times 4 plus 3 times 7. So 1 times 1, that's 1, plus 8, that's 9, plus 3 times 7 is 21. So 30. So that's how we get the 30 that we see here. So then this one is going to be 2 times 2, no, 1 times 2, 2 plus 2 times 5 plus 3 times 8. And that's why we get the 36 here, because that's 4 plus 10, so that's 14, plus 24. Is that right? 3 times 8 is 24? Oh, now I've got my math screwed up. 2 times 8 is 16. 16 plus 8 is... Yeah, that should be 24 plus 14. So let's do 24 plus 14. I had 38, so that's definitely wrong. Well, my math in here is incorrect. But I guess that's the idea. Let me continue. Three times 11 plus 4 times, oh wait, is this the first? Okay, so I'm wrong with that. This is the first item of the first array output. And then the second is going to be 1 times 12. Okay. So our output is then going to be 1 times 2 plus 1 times 2 plus 2 times 5 plus 2 times 8. So this is 30. This is 2, 10, so that's 12 plus 16. 16 plus 10 is 26, plus 2 is, I have 28 here. So that's also wrong according to my math. So we take a look at the output again. It's yeah, so I haven't, it's not like I did, well, with it, did I do it for different one? No, it's like, I've got the same math here. So this one is correct. The 1 times 1, 1 times 2 times 4, 3 times 7. Miguel, hello, good morning. Oh wait, 3. 3 times 8. That's what I needed. So 2 plus 10 is 12, plus 24 is 36. Okay, now the math works. Silly math. All right, so for this one, it's gonna be 1 times 3, 2 times 6, plus 3 times 9. So that's 3 plus 12, that would be 15 plus 27 is 30, 42. Which is correct. That's what we have here. Doing some Python. So I caught up to where I was in a book. So I switched over to Python temporarily to follow the book example and then actually figure out what's happening. And then we can switch over to JavaScript to do it all manually in JavaScript. But in order to do that, we need to fully understand what's actually happening behind the scenes. And actually, I find that this is an excellent way of learning because it forces me to really know this math first. Kathy Royale, good morning. Is there a chance to paste you a code on Traceman and you try to solve? Not right now. I've got this that I'm trying to focus on. So I don't have the time to work on that. Maybe in a couple of weeks, I'll be able to do something like that because I will, I'll be done with the conference talk. So thanks for thinking, but unfortunately I'm not, I can't distract myself right now. Can I remind you what book I'm using? Yes, I can show you the book. It is this. All right. So, yeah, I do like in the archive of the YouTube videos, I've been putting the link to the book. I think I've been putting a link to the book. I just sort of been pasting in now. But okay, we now understand what's happening and why this is happening. I guess the next question is, why are we getting 4? Because like why we can have this if this is 4 here. 7, 10. It's on GitHub too, but the 5 final chapters aren't there. Yeah, I think I saw that before. All right, so if I do this, the first 3 are exactly the same, and then we have 48. So we had started with this here for the 30, this here for the 36. Oh, it's because it's 1, 2, 3 times each of these. 1, 2, 3 by these. 1, 2, 3 by these. 1, 2, 3 by these. So that's this ends up adding like the next section. So this isn't exactly correct the way I laid out these comments. So I should remove them and move them up to here. So then the last one would be 1 times 4 plus 2 times 7 plus 3 times 10. So it is a slightly different way of thinking, but it works the way sort of intended. And it looks like it's the opposite of, well, maybe not the opposite, but it's taking a vector and a matrix and turning it into a vector that has the length of the width of the matrix. All right, so what is this? This is 4 plus 14, so that's 18, plus 30, so that's 48. Which I got it right. All right, so now that we know what is happening there, that's what this is doing. Then we're riiluing this. So this is interesting. Riilu is a function x that then returns this. So I kind of want to now print layer 1. So we get a full number here. -0. It's always funny when I see -0 in programming languages. They can actually be the cause of many bugs too, because -0 I don't believe is equal to 0. So we have -0, -0, -0. So this is the 1, 2, 3, 4. So this is the width. So what I kind of want to do is print layer print the result of this before. All right, so this is the result of our the dot, and then this is the after effect. So if we take a look, this is a negative number, so we get a -0. This is a negative number, so we get a -0. This is a positive number, so we keep it as a positive number, and this is a negative number, so we get a -0. All right, what does that mean for us? It means that let's see. Change all values in the vector, or I guess it's do the dot and then change all values in a vector. So dot the vector and matrix, and then what is this? This is, and then change all negative numbers to 0. All right, so we do that. We have this vector of either 0 or positive numbers that is hidden size wide. So that's going to be our new inputs. We then dot those. So that's our layer 1. We dot those with the second set of weights, which are just completely random as well. And we get the result of that. Now, my guess is that we're going to combine these together. We're going to combine these together with the predictions and everything else. So I think this is our ultimate prediction. Oh, right, because the very next page, we start talking about back propagation. And from what I can see in here, so I read through a bunch of this last night, but like a first pass of reading through, there's a lot more to sort of like dive into it deeply, which is why I do this too. Is the first one forward propagation? No. Back propagation, and then later forward propagation. It looks like there's a new riilu to derive here. Before I go, I'm going to save this and put these on up. So deep neural network in Python. Okay, so what do we have here? We still have this riilu, but we're gonna add this derive riilu to derivative. I'll just keep their names for this, but he's not even following the underscore like the snake case. This takes an output. Interesting. So he just has return output is greater than 0. That's returning true. That's not returning 1, unless 1 and true. Hold on. Python 3 is true equal to 1. Oh, huh. Okay. Well, there's that. So if I take true plus 1, I get 2. All right. Well, that's why that works. Yeah, they do seem to be interchangeable. So this is return 1, true 1, if output is greater than 0. In JavaScript, we'll have to be slightly differently. Bit unfortunate, in my opinion. Yeah, it's times like these when I sort of like turn and stare at the people who like these languages, but then make fun of JavaScript for its quirks and go like, so you're gonna make fun of another language for doing some quirky things with triple equals and double equals, huh? Let's take a look at your true and false. I think in the end, all languages have weird quirks, and you can do all sorts of amazing things with every languages, and they all have things that make them suck, but they all have things that make them really awesome too. All right, so what's next? I need like a book holder, like something like that, but I don't have one. I mean, I guess I could on the other screen get the digital copy up too, because I do have that. That is something that's nice about the Manning books, is that you can get the free digital copy. Okay, so we still have the alpha. We still have our hidden size. Though, interesting. He forgot to put the streetlights in here in the full edition. I'm not going to delete it because we need it. Let's see. We have our alpha. Oh, we have our alpha. We have our hidden size. We have our weights created. And then I'm just going to down here, and then we'll move which ones we need to down. So for looks like, oh, he's only going to count 10 times. So for count in range, he's going to go 60 times through this. Thinkalum, good morning. You have an IHD 105 transparent book stand, and you love it. I am going to write that down. IHD 105 transparent book stand. Yeah, if I do many more books, then I'll definitely want to potentially like start looking into a book stand, especially if I do these on stream where I'm not allowed to actually show the book because I own a license to it, but obviously I don't have a license to show the content of the book off. Also, I do know that it's 8:12 a.m., but Friday are work from home days for my company, so I'm gonna continue working on this a little bit longer than normal. I just don't have to do that entire travel thing. All right, so what do we have here? I think what we're gonna do is just go through this example and see if we can get it to run, and then move. Then I'll probably bring the stream down. So we have our iteration range 0. Then interesting. The first thing we're gonna do is count the totals. So layer 2 error. So this is our total errors for the final prediction. Then we're going to have another for loop. So for I in range, we're going to go through the length of streetlights. So we're gonna get the index and loop through each of these. And the reason why we're not just doing for streetlight and streetlights is because we also need the index here. I don't think there's a way to grab the index here, right? Like I can't do for street light I. Can I? What is this? It would be for thing index in, it's just array of like 1, 2, 3. Can I print thing index? No. Okay. That would be super nice. That's one of the things I miss about Rust, is that I could basically just do that over my loop. But okay, we'll do it this way. Where was I? For count. For I in range length streetlights. Then we're gonna go through the entire like prediction thing here. Yeah, for x, y, and enumerate. Is enumerate a thing in Python? Ooh, hold on. Enumerate 1, 2, 3. Oh, it's the opposite. Index is the thing, and the value is the opposite way. Oh, that's so nice. Let's see. Can instead do for index streetlight in enumerate streetlights. There. That would be, this would be so much nicer if I could do that. But all right. Thank you, Miguel, for that tip. I do remember also that's the way to do it in Rust, is the enumerate. So we get our layer 0. Our layer 0, so this is the first round of predictions. This is essentially going to be this. We get our layer 0. Is equal to streetlights. This drives me crazy. He does this, I:, I plus 1. So now I need to look that up. Okay, so if I have my array 1, 2, 3, 4, 5, array of 0, 1 is just 1. Oh, that's interesting. Does it return an array? Is that why? Okay, hold on. Result equals array of 0, 1. The result is an array. Right, so it returns an array. So that's what he's doing. He's making sure he gets an array out of it. I mean, I'm not really sure I like the syntax for this. Let's see, returns an array of 1 value. Then we go with layer 1. And riilu np dot layer 1 weights 0, 1. So it's going to be the exact same thing here. So we're just going to dot the matrix and get that 4 wide outputs. So this is basically getting our first layer inputs. This is our first layer outputs. Katali just came back. We're working on the back propagation in code. It's going to be our last sort of example here. We're still in Python. Let's see what's next. Then we're going to get our layer 2, which is this full dot. I'm really sad that it's not auto indenting for me, which like VS Code does for that for me in JavaScript, which I don't see why it couldn't do that here in Python either. Okay, so we're gonna dot those the exact same way. Now we're going to calculate the layer 2 error and increment this value. So we can, just like we did in that first example, we're going to see what are the total errors across the entire predictions, all the predictions. And a prettier, like prettify. I need to install auto pep 8. I can do that. Python auto pep. I mean, sure, let's try it. I mean, it didn't do anything. Oh, it's a pip pack. I don't have that pip, so it's probably not going to be happy with me. All right, I'll deal with that later. Auto pep 8. I'm sure the next time it'll open up, it'll yell at me because I don't have it set up properly. All right, so we're going to take the error and we're going to add to this one. So layer 2 error. So this is incrementing by a numpy sum. So that's just summing up the contents of a vector. And we're going to take the prediction, so this final prediction, which is layer 2, and we're going to subtract the output that we were supposed to be getting. The output being this did walk versus stop. And of the index. Oh, they're doing the same thing to turn it into an array, to turn it into a array. So instead of just like the actual value, it's an I plus 1. Right, we're going to take that entire thing, and for each of them, before we numpy sum them up, we're going to multiply it by itself. So we're going to take to the power of 2. So I guess a little bit more to unpack here, but when we go to JavaScript, we'll make this into just its own thing, like several different lines, and tested. All right, what's next? We're going to get the deltas now. So we have to get layer 2 delta, so that makes sense. Layer 2 delta. Because we just have a single output, this should just be a single number. So that's going to be our prediction versus what really happened. They have it backwards here, which they're wrong. The book has to be wrong here. So it's going to be another numpy. Oh, it's not a numpy sum. It's just. I like how they put this in parentheses, but I don't think it needs to be in parentheses here either. It's not a tuple. So we're just saying the layer 2 prediction subtracted from did walk versus stop, and then they're doing the same. I plus 1 here. Okay. Layer 1 delta. So this is going to be the interesting one. Layer 1 delta. We're going to take layer 2 delta. Oh, interesting. So they're not using numpy to run the dot here. They're going to do it off of this object. I assume this is an object, and that numpy was sort of like constructing one for us. It is like a factory function, but I don't actually know for certain. So they're saying, okay, we're going to do layer 2 delta, and we're going to dot off of it the weights for 1, 2, and we're going to translate that. We're going to take that entire result and multiply it by the riilu to derive of layer 1. So this is something to unpack. So layer 2 delta dotted together with the result with a translated 1, 2 weight. So if you remember, it's a matrix that looks sort of like this, but because it's translated, 1 stays in the same spot, but the 2 is now here, the 3 is now here, the 4 is now here. So it's 4 down and 3 across. Transposed, okay, that I need to make a note of that so I say the right things. So dot together layer 2 delta and a transposed layer 2 weights. More communication about that bug yesterday. Layer 2 weights. And then multiply that. Result with, and the riilu to derive is, this is allowing all the negative numbers. So return true 1 if output is greater. So if the negative numbers get to say what they are, and the positive numbers turn into 1s. I think that's what that means. So for example, output is like -5 greater than 0 is false. Oh, wait. It's turning things into 0 or 1. That's all that's really happening then. Because this is going to return false or true, which in Python is 1 or 0. So it's going to return 0 if it's less than 0, and it's going to return 1 if it's greater than 0. That's it. And multiply the result with layer 1 prediction. Oh, layer 1 is the prediction, the first prediction from the first neural network. Prediction, but with its values turned into 1 or 0. Depending on if they are positive, 1, or negative, 0. That is what this line is doing. So then we get our layer 1 delta. And now we update the weights. So our weights, they have, interesting, they do the other weights first. So weights 1, 2, we're going to just use NumPy to sort of add these in here. We're going to take the alpha, so this is going to be a scalar these deltas, I think they're matrices now. I think they are. You have to do first the output. Where does that do that? So it goes backwards. Well, yeah, that makes sense. I'm just, oh, right, I have to do that one because to go backwards. Although doing this math, it doesn't feel like it's that different from each other, unless these are mutating. All right, so we're taking alpha. We're going to multiply layer 1, but we're going to transpose it, take that result, and dot it with the layer 2 delta. So that's a lot to unpack there. Then the weights 0, 1. What's also interesting is that suddenly we're adding the weights in, whereas previously we've been subtracting the weights. So same thing, we're going to take the alpha. We're going to multiply the layer 0. So layer 0 this time, we're going to transpose it. And then we're going to dot the result with the layer 1 delta. All right, so that's this, and then they have us. So I should mark down what these are doing. So replace weights. So replace or like add two weights. The result of, so it's going to be a scalar alpha. So alpha being multiplied by the transposed, so the transposed layer 1 dotted with the layer 2 delta. So what does that mean in reality? It's going to do this one first. So we're going to first transpose. So we take layer 1 and we rotate it like that. And then we're going to dot that together with the layer 2 delta, which we created up here, which was simply just a subtraction between the prediction of layer 2 and the single array item. And then we're going to multiply that with alpha to get our new matrix. So this is going to give us a matrix in the end. Then we're going to multiply that by alpha to limit it. So we get, and then we add that to weights. And then we do the same thing here with these weights with just layer 1 delta and layer 0 being transposed. And not in this inner for loop, but in the first for loop, we want to count. So if our count modulus 10, so is equal to 0. So oh, that's hilarious. He put 9 in there. Every 9, I'm going to do 0. Every 10 loops, we want to print the error, and we're just going to have the layer 2 error. And let's run this. Let's see what happens. Runtime warning. Okay, so it kind of worked a little bit, and then we got a bunch of not numbers. Invalid value encountered in greater return x. So that's the riilu. And the riilu to derive. So both of those had an invalid value encountered. Well, that's lovely. It didn't tell me what that invalid value was. So what I'm going to do is, these are just warnings though. They didn't actually help us out. So let's pause on each of these. Start debugging. Wait a second. Wrong file. Not mnestraining.js. We want this to be what? This is so wrong. Don't save. Add configuration. So Python. Hold on, I'm not in the right Python file. Okay, you go away. You go away, don't save you. Streetlight. This is what I want. Oh. Add configuration. All right, this is totally not working the way I wanted to. I know I'm passing something that's not a number. I just don't know what I'm passing. That's not a number. So Python. Yeah, that's totally what I wanted you to do. Don't save. Let's try this again. Debug. No, okay, so hold on. I need to figure out how to, I'm just gonna remove this configuration. There. There you go. Now we'll start over again. Debug, start debugging our current Python file. Here we go. I was saving the file, but it had like the old configuration in it. So I'm like, I'm done with you. All right, so I can go into our debug console and we can start playing around with this. So our first X is a full array. Is that? Is a full array. So that's not cool. Yeah, an array greater than 0, that is not going to work. Well, wait, no, it will work, won't it? Because it's a numpy array. But this is an array of arrays. I kind of want to just step. But now what is riilu layer 1? So let's take a look at what layer 1 is. Okay, so that worked the way we expected it to. So now we're in here and output is an array of these things. So it's this array of arrays here. If we step over, where was that riilu to derive? Right here. So layer 1 delta. That's what we expect it to be. So this first time through, I think, is fine, but I think the weights are about to get screwed up. It's easier for me to just type this in here. Weights 0, weights 1, 2. Look at that, new lines. I don't know if that's good or if that's okay or not. And then I'll step over. So let's take a look at weights 0, 1. That's still okay. All right, so let's continue into our next breakpoint. This is the same thing. It's an array of these items. Output is the array of these items. just an array of negative zeros. We haven't gotten the warning yet. So all of these things earlier, you are still okay. You're an array of 0 dot. Wait a second. Okay, so you're just -1. Array of 0 dot. Delta is an array of zeros now. We're about to update the weights. Fine there. Now, our error is the one that's sort of being so this entire first time through, this is okay. Let's go into there. X is still an array. Output is still an array. Still an array. An array. And so we got our first error printed out. There are 2 errors, still a thing. When we got this first error, and then we got a runtime warning before the second error. I'm not seeing anything so far. So before the 10th one, really. What's our count? Our count is 3 still. Whoa, crap. What is output? Output is now an array of nan. All right, sometime in the 4th time through, everything went underflow. I'm not invalid counter and greater return output. I'm not underflow. Oh wait, did the number get too low? That's what you're suggesting. Yeah, that's an interesting question. If I go to streetlight, if we stop this, if I do the number that they're using, so np random seed, and 1, do we not get this error because it's the exact same random seeds? numpy, not mp. So we lasted longer before we got the error. I should need an error checkout to break if it's low enough. Yeah, well, I mean, it sounds like I need that. Of course, we don't have that here. If I iterate through this less times than 60, that would, like, you know, no doubt help. But this error is going towards... It starts at 1.4, negative 1.4. It goes up and then sort of back down to negative 1.4. So yeah, you put an error checkout in. Their code did not. So I think what I would need to do is put an error checkout in there after each loop through. So after each time through, I was gonna like point towards the book, but that's not helpful. So each time through here, at the end of each loop here, check my error. And if it's gotten small enough, but I don't actually think that that's the thing. Your alpha is larger than you want. How can I see that? I want to visualize this. I think I can predict the alpha is times the weights. The end result error, the layer 2 is my end result prediction, right? So I can do print prediction is my layer 2. And this is the did walk for a stop of I. Look, the error, you're getting bigger. Yeah. Well, I got bigger and then smaller and then bigger, but that does seem like the trending towards that. So that's another reason for potentially using the random seed here, and why I don't necessarily like doing that. I want to see this first. So here's our expected outcome. Our prediction 0.3, our expected outcome, and then it gets really small, even smaller. And I can see it's not working the way we want it to. 0.1, 0.1. Here's this gets really, really small. Is there anyone where it wildly swings up and gets really big for just like extremely small? Not really. The errors are sort of like swinging, but the because we're seeing the errors swing a little bit. The predictions are swinging between like 1 and like way small number. So I'm wondering if I set the alpha to 0.01, way smaller. No problems now. We see this prediction 8 for 1, a smaller number for 0. 0. This prediction for expected outcome, that's not good. Prediction for expected outcome, that's right. I don't know why these are sometimes there, which is that's not what we want. Our error the last error that we got was this one, negative 1.8, negative 1.87. Oh, it's just error colon. Do I have another one of those? No, not really. So negative 1.87, negative 1.80. So it's actually going the wrong way. Negative 1.7. I want it to go towards 0. That is also interesting. The error is negative. And so, where is this? Numpy sum. I think there must be a bug in this code. You get a single prediction that always goes towards 0. Even if you're trying to go towards 1, because that's not necessarily what we want to do. Menacing parentheses. I've got the thing on, so if you find it, let me know where it is with the bang line. Is it this? No. $55. Okay. So number sum, open. I mean, so I open the parentheses here and I close it here, but do I want to close it here instead? Another set of prems for these, I bet. Like that. Oh, yeah, they did have that there. I just totally missed it. Let's try this. I'm going to remove these prints. They're not helpful to me. This is still 1.3. This is going up. The errors are going up, which is not optimal. But you sent something. That's my call to go down and do some stuff. Get some breakfast, and actually it's work time for me. So I've got to go and do that too. We have this code. I can. Oh, really? Okay, I can do this. I'll be done in a second. And then I'll be down. Let's touch Katali solution.py. Paste you in. Here you have your break. Let's see. Your error is 3. Layer 2 error. You have your prediction of the layer 1, layer 2, and then expected. So expected is 0, and that's a very small number. These are all the same. All right. Unfortunately, I'm out of time, so I can't figure this out fully. I may have like copied pasted this wrong. Or maybe I shouldn't be using Python 3 on it. I don't know. It's not working on my computer. I'll have to figure this out. Anyways, thank you everybody for stopping by and watching. I can switch over to the big one here. So what we did today, we sort of went through, we started kind of getting back propagation working. We have a little bit more to work on that with that. I'm going to continue working on this because I don't have time to only do this on stream, then also get ready for the conference. So I will continue working on this. The next planned stream is on Sunday morning at 7 a.m. Mountain Time. That's the pair programming with Kale. We're building a PHP application with Laravel. The next planned deep learning stream is on Monday morning at 6:45 a.m. Mountain Time, where we'll continue with whatever I learned this weekend. I am also archiving these all up to YouTube. So if you missed part of this or you want to see the others in the series, I have a link to the YouTube down below. If you like this and you want to get notified, please follow me here or follow me on YouTube or on Twitter. I tweet out when I'm going live too. Anyways, that's all I've got. So I am going to head off and have a hopefully great day. And I hope you all have a great day or night or at least a weekend. And with that, I'll see you next time.